Hello everyone, I'm Yuqi Chen from Singapore Management University. Today I will give a talk about my paper, Active Fuzzing for Testing and Securing Cyber Physical Systems. At first, I will introduce what is cyber physical systems. As the name suggests, CPS can be divided into two parts, the cyber part and the physical part. The cyber part is the distributed software components, and the physical part is physical process. From the graph, we can see these two parts are intertwined. The cyber part will get the sensor reading as the input and control the behavior of actuators to influence the physical part. Then, these are three examples of CPS. The first one is the water treatment plant. The second one is the smart grid. The third one is the autonomous vehicle. CPS are commonly used in the critical area. The threats of CPS will cause significant consequence. These are the examples. These are the real threats of CPS. And these threats have motivated research into countermeasures. For example, anomaly detection, fingerprinting, environment-based monitors. However, assessing the different countermeasures for CPS is not always straightforward because of the need for a realistic set of attacks to evaluate them against. We have a new issue here. Where exactly should such a set of attacks come from? Typically, the attack set is constructed by some experts or from a hackathon, which takes a large amount of human resources. Then, in order to solve this, I will present Active Fuzzing, an automatic approach for finding test suites of packet-level CPS network attacks. The basic idea of our approach is simple. Once we get the fuzzer, we only need two inputs. The first one is the current network traffic, and the second one is the attack goal. Then we can use our tool to generate the attack, which can manipulate the network packets to achieve the goal. In the following, I will introduce our case study and show you how it works with one example. Okay, this is our case study SWOT, which means Secure Water Treatment Testbed. It is a scaled-down version of a real-world water purification plant, which is located in the ISSTA lab in Singapore University of Technology and Design. This is the system overview. From this figure, we can see it is a complex real-world critical infrastructure testbed with lots of sensors and actuators. So you can find a lot of pumps and wells in this figure. Then I will show you one example of the attack generated by our tool. This graph describes the relationship between some interconnected components across the first three stages. The attack goal is to overflow tank LIT101. These actuators are related to the this tank level. Once we set the goal, our tool will manipulate the packets to open MV101 and close MV201, which are both valves, and close P101. Then water will flow into this tank. If we achieve the goal, you can see what will happen. But we cannot always do this because it takes around 2 hours to clean the water. So typically we just set a threshold. And if the sensor value reaches the threshold, we think we attacked this sensor successfully. Then I will introduce the network architecture. Due to the time limitation, I only introduced the level 0 here, which is the lowest level of SWOT. Network attack in this level may change the behavior of actuators directly without dealing with the logic of the PLC and maybe some defense mechanisms in the higher level. Then I will implement my intermediate attack between the PLC and the remote I/O. This connection is in the level 0. Okay, after we implement my intermediate attack, we can get the network packet like this. So how to deal with the packet is a new problem. Luckily, we can use the tools such as Wireshark or Scapy to dissect the header information of a level 0 SWORD packet. Because SWORD implements the Common Industrial Protocol over ENIP protocol. After dissection, we can get the payload of this packet and the corresponding IP address. Actuator commands are encoded in the payload of this packet, but you will see it's still a very long series of numbers. We still do not know how to manipulate this packet. So we need a model to help us to figure out the relation between the sensor value and this number. Then I will show you our assumptions and the limitations. We need to train a model under these limitations. We do not have a pre-existing dataset. We do not have a priori knowledge about the meaning of network packets, and the time is limited. However, we should have the assumption that we can get access to the level 0 packets and observe the sensor value. Otherwise, we cannot manipulate the packets, and if we cannot observe the sensor value, we do not know whether our attack is successful or not. This is the overview of the training. The basic idea is that we train a model based on a small number of data and improve the model based on the living data from the system. In the following, I will introduce what is the prediction model and why we have to do this. Okay, this graph is the prediction model. From this graph, we can see the prediction model can predict the sensor value or the change of the sensor value based on the network packets. There are 16 types of packets in 4 stages. We combine all of them and get the feature vectors with a long series of 0 and 1. So the number of potential combinations is huge. Which also shows that if we randomly flip the bits, it is hard to change the targeted sensors. And we use 2 kinds of models here. One is the gradient boosting decision trees, and the other one is the linear model. We use the linear model as our baseline here. Both models can be integrated with existing active learning frameworks for regression. So if we have the prediction model, we can manipulate the packets offline and find out what will happen. And then we have a new question. How long the attacker must spend pre-training on normal sensor readings? Okay, this is the result. These numbers are R2 scores of linear and GBDT sensor prediction models after different amounts of pre-training time. So the number is higher, the result is better. So after 3 hours, we can see GBDT outperform linear model in most cases. Regarding the pre-training time, we fix it at 14 minutes. Because our models show some positive correlation here. But you may find some scores are still low, but this will allow us to assess whether active learning is still effective when applied to cases that lack a good pre-training model. Once we have the pre-trained model, we need to do is to test and improve the model. So we have to add new samples and observe the new sensor values and retrain the model. We use two algorithms here to select new samples. Since it is an online learning, so the idea is that we will flip a certain number of bits based on the current network traffic and find out the cases may maximally change the model itself or maximally change the sensor values based on the existing model. Then I will implement my in-the-middle attack to replace the current network packets and observe the new sensor values. Afterwards, I will answer the following two questions. How long the attacker must then spend active learning? Why we have to do this? Why not just train a model with a large amount of time? Okay, we should answer the first questions. From the table, we can see once pre-trained on 14 minutes of data observations, attackers can accurately predict SWOT sensor readings after 10 to 45 minutes of active learning. And we can see typically the tank level is hard to predict, so it takes longer time. Before solving the second question, I would like to introduce how to discover attack. The first step is to sort the features based on feature importance. In the following, I will introduce what is feature importance. The second step is to define a suitable objective function for prediction value. For example, if we want to overflow a tank, the objective function for this tank is the tank level itself. Then we generate a candidate by flipping fixed number of important bits to maximize the objective function. In this step, we should search the bits from most important features first. Since it is online learning, we should finish all this in a short time, otherwise the current net traffic will change. Once we find the strategy to change the network packets, we should manipulate the packets in the real system. This is the concept of feature importance. We just assign a score to input features based on how useful they are at predicting our target variable. Then I will solve the second question, why active learning is essential. We use the same example here. We try to overflow tank LIT101. Now there are two GBDT models of LIT101 here. The first one is the pre-trained 14 minutes plus 10 minutes active learning. The second one is pre-trained 90 minutes without active learning. The horizontal axis here is the index of the features. As I mentioned, we should use this model to find the critical features to discover the attack. Otherwise, the time is not enough if you just search, for all the features. So through observing, I know these three features will influence these three actuators. So we will find the first model find all the critical bits. However, the second one only find 591, which is related to M101, and you will find there are a lot of features with a higher importance than this. But there is one issue, so we know the R2 score of both models are larger than 0.9. So through this experiment, we know that R2 score only represents the correlation. Only through active learning can you find the real critical bits. In the final, I will find which model and active learning setup is most effective for attack discovery. In the table, we calculate the successful rate by running our active fuzzer 1000 times with the given model. Then we record the percentage in which the modified packet would cause the physical state to cross a safety threshold. We can draw a number of conclusions here. First, since the search space is huge, the successful rate without a model is almost zero. And as I mentioned, if we do not use active learning, the successful rate is very low. And then I compare the performance between the linear models and the GPDT models. And we can see linear models are not expressive in general, and the GPDT models outperforms linear models. However, like the linear models, GPDT models also struggled to attack the LIT sensor values for a small number of bit flips. But you can see it can attack them all once the restriction is lifted to 10-bit flips. One more issue is that we can see the successful rate for LIT301 is low for all the models. The reason is simple, because this sensor is involved in lots of processes in the system, which means we should change more commands to attack this sensor. This is the evaluation highlight. Through the experiment, we prove that L2 Faster is effective at identifying critical bits in payloads and can lead to significantly higher successful rates in attack discovery. And this is the take-home points. In this paper, we propose a black box approach for automatically discovering packet-level network attacks on real-world CPS. And this tool doesn't need a pre-existing dataset, prior knowledge about the meaning of their payloads, and a large amount of time. So we evaluate our method on a real-world critical infrastructure testbed and prove active fuzzing is essential. And that's all. I'm open to any questions you have. Thanks.